Hi, in this video, we're going to take a look at estimating the LD50 of a medication using a Bioassay experiment and Bayesian statistics. All right, the situation that we're in is that for a pharmaceutical, we need to figure out what is the LD50 of the medication. So LD50 is the estimated threshold where half of people receiving a certain dose will die if they're exposed to this. All right, and this is a benchmark for assessing how toxic and poisonous something is. All right, so in these experiments, these are very expensive. There's ethical concerns, and these can take a long time. Also, it'd be very, very expensive, time consuming. The ethics of it, the optics of it. So you're probably not going to get a whole lot of data. Now, this is data taken from the textbook. I was not part of any experiment of this nature. I just want to show how we could proceed if we were in this situation. All right, so in our data, we have the dose level, which is in logs. It's the log of grams per milliliter, number of animals, so number of trials from a binomial point of view, and the number of deaths. Okay. And so what we want to do, we want to use the data that we have to make an assessment. Now, there's a problem with this. All right. The optics, the ethics, the time consuming aspect, and the money makes it so that we don't have a lot of data. All right. So I don't have a lot of data. This is a great time, or not really a great time, but this is a very appropriate time to use Bayesian statistics. What we're going to do, we're going to use our subject matter knowledge. We're going to use our subject matter experts to fill in the gap that our data does not provide. All right, so let's say that this is our actual data. So we've got 20 actual observations going on, and we have the dose level, the number of subjects that receive that dose, and the number of deaths from that dose. Okay, so what we're going to do is we're going to go and we're going to use logistic regression, and we're going to get an estimate of what's going on. Now, you look at that sample size, that's not a lot of data. No, no, that isn't very much. So let's go ahead and let's fill things in where we can. So let's review logistic regression. So what we're going to do, we're going to say that the number of successes is going to be binomially distributed with the number of counts and the probability of success for each one. And so now P is going to be the probability of success. 1 minus P is the probability of failure. And the log of this ratio, which is odds, so this is the odds, the probability of success over the probability of failure. The log of the odds is equal to this thing that looks like regular old, linear equation from college algebra. All right, so now if we were to use a flat prior, so there the prior is I have no prior information, I have no knowledge, no idea of what's going on, then our prior distribution would correspond to the likelihood function, which we use every regular time that we do logistic regression. So every time I do logistic regression without specifying a prior, it's equivalent to specifying the flat prior. Right. So under the hood, when we do logistic regression, our model is fitted using maximum likelihood estimation. And so what we're going to do is that we're going to take the likelihood function of beta 1 and beta 0 is going to be equal to the probabilities. And you notice that this is, I'm just dropping my p's, my y's, and the n's into the binomial distribution formula, and then I'm taking the product of it. Okay, and so then I'm going to, uh, so with this, what I want to do, I want to find the beta 0, beta 1 that maximize this term here. I want to maximize the likelihood when I know what the X values are. So there's several layers going on here. And under the hood, we can go in and if you can study up on this. For our purposes, it just works out perfectly. Not perfectly, but it works out almost like magic almost every single time. Okay, so let's go ahead and let's just do classic maximum likelihood estimation. So here are the X values. So these are coming from my original data set of the dose. All right, and then I'm going to have my number of deaths. I'm going to have my sample size. So here's the sample size for each dose level. And then here is the number of deaths. So even to be morbid, we're going to say that death is a success for this purpose of modeling. Remember that when we do the binomial distribution and Bernoulli distribution, success and failure is just like the default language that we use and here we're saying death is success just to make the math line up. Like you and I, we know that that's not a success. That's a bad thing. Makes me sad. Okay, so my data is going to be the number of deaths and the number of successes for each level that we have. And then my predictor variable is going to be the dose aspect. So here, notice that I've got in this data set here, I have the number of deaths in the first column. I have the number of survived in the second column, and that's inside the formula on the left-hand side there. So I have a two-column data frame on the left of the tilde, and then I have the predictor variable value here. Okay, so when I look at this, notice that as the dose increases, just looking down the line, we're expecting to see a positive correlation between dose and death. As dose increases, the number of deaths increases. Okay, and so I'm expecting a positive coefficient out from my model for the slope. If I don't see that, I know that something's off, something's weird. I have a misunderstanding. I did something wrong in my code. I can, dig into it. So let's take a look. All right, so I see that I have a positive coefficient, and so there, that fits. Now, does that make sense? I don't fully know. I'd have to like draw it out and do things by pencil and paper mathematics. But that's where we're at. Now, all right, we'll notice that neither the intercept nor the slope are statistically significant. All right, well that's not really good, right? You know, what reflects is that I don't have enough data to come up with a solid conclusion. All right, now these experiments are super expensive. They're super, super, super time consuming, lots of issues, ethics, optics, lots of things going on. If I was a statistician working on this, I can't just say, oh, it's not statistically significant. I need to come up with an answer. I need to find a way to come up with a reliable estimate of the LD50. Okay, so what I'm going to do now is I'm going to, instead of doing a classic approach, let's go ahead and talk to the subject matter experts. So let's talk to the scientists that are involved in this who will know what's going on better than I do. Okay, so I'm going to sit down. I'm going to, try to convert their knowledge of the situation, their knowledge of the toxicity of the medication, into a mathematical statement. Okay, so when I'm talking to them, let's say right here, this p equals zero point 0.5. What this says is that 0.5, that is the median of the distribution when we're at a particular value. So the idea here is that when the dose is negative 0.7, so that's a fixed value. So let's say that I'm talking to my subject matter knowledge experts, and they feel like they know what would happen when the dose was negative zero point 0.7 and positive zero point 0.6. Okay, so I can figure out from them, just talking to them, that they're confident in making an estimate at those two values. By the way, it can be extraordinarily difficult to get this type of information out of subject matter experts because this isn't how they think. They don't have that math brain. That's why I'm getting paid. So I've done this with education, not with toxicity, by the way. But talking to your stakeholders and getting information out. Sometimes you have to be very patient. You have to, work with them, try to pull out that information, and take some steps to convert what they're saying into mathematics. So I'm talking to them, and I'm able to get them to be able to say, all right, I feel comfortable making a declaration about negative zero point 0.7 when that's the dose and when the dose is uh, positive zero point 0.6. All right, now when we're talking about negative zero point 0.7, I'm talking to them and they say, you know what? I feel like the median of the distribution should be around zero point 0.2. Okay, so the median of the beta distribution should be around zero point 0.2, and the 90th percentile should be around zero point 0.5. Now, it would be very difficult to get a non-statistician to speak in this manner, but this is what I need to do to be able to get this information out of them. Okay, and so it'll work out that since I've got an intercept and a slope, two unknowns, and now I've got, I can, ascertain, I can set it up so that I'll have a system of equations to fit these two values. So I'll have I'll just drop it straight into regular old logistic regression equations, and I can figure out estimates of beta 1 and beta 0 off of this. But I'm actually going to need two spots. So this information is for x equals negative zero point 0.7. Let's talk about when x is equal to positive zero point 0.6. Once again, I'm going to have to talk to my stakeholders, talk to my subject matter experts, and when x is equal to zero point 0.6, the dose is zero point 0.6, they feel that the median of the beta distribution should be at 0.8, and the 90th percentile should be at 0.98. Okay. Awkward conversation. And honestly, this would be more awkward than any conversation I've ever had when I was doing Bayesian statistics, in actual practice. But you can do this, and you can get this information out of them. It's just that you have to really know your statistics. You have to really know, and understand how to take their words and put it into a math equation. And that's on you. That's your responsibility in this situation. Okay, so what we're going to do, we've got percentile statements, or sorry, quantile statements about the beta distribution at two different doses. I'm going to drop these into the first dose location of negative zero point 0.7. I'm going to drop these into the dose location of positive zero point 0.6. And what that's going to do is that it's going to estimate, both of these are going to be estimated alpha and beta values for the beta distribution of the parameters at those two doses. Okay, and so now this is my prior information. Here is my X value, so the dose, and then inside here, which I've got hidden, is going to be the alpha and beta values at the two locations. All right, so now what I'm effectively going to do is I'm going to pretend that my prior is actual data. I'm going to combine it with my data and then proceed forward to obtain what I actually want for this. Okay. And so here you can see that I'm taking my actual data and I'm appending my prior distribution knowledge onto it, and that is data.new. Okay, so now let's go ahead and visualize what our prior actually means to us. Okay, so the first prior that I have, which is at dose negative zero point 0.7, is an alpha of 1.12, a beta of 3.56. When the dose is zero point 0.6, my prior is 2.1, and my beta is 0.74. Okay, now the the larger the alpha, the more we're saying that there will be a so the larger the ratio of alpha to beta, the more likely there is to be a success. In this case, a success is death, which I don't know how that's a success, but that's just how statisticians talk about it. All right, and so now let's go ahead and visualize this. All right, so all this code is just to implement all of this. And now let's take a look at the picture. Okay, so here is my prior distribution at negative zero point 0.7. Here's my prior distribution at negative point, or so positive zero point 0.6. And you can see this is, I think it's the 95% quantile range, or maybe 90. I forgot what I put in there, but it's a reasonable quantile range. You can see what the central tendency is based off of my prior. Putting this into the GLM function, I can get a curve. Now, you notice it's not perfectly passing through those dots, but it's pretty close. It's reasonable. And so this is my generalized linear model, my logistic regression based off of my prior knowledge of what's happening. Okay. And so this is like from a classic Bayesian point of view, I would have actually started with my prior, then collected data, then combined them. But in this situation, we got data, we looked at the results, we said it's not good enough. Let's see if we can do better using Bayesian statistics. Okay, so now what I want to do, I want to combine my prior with my data to get my posterior distribution and to get a better estimate of what's actually happening. Okay, so what I'm going to do is I'm going to take the data that I have with my prior, so that my observed data and my prior together is my data.new, and then I'm going to go through and I'm going to figure out a contour for the distribution of the coefficients. So remember that this is a multivariate problem. I have an intercept and a slope, and I cannot assume that these are independent. Since I have no reason to think that they're independent, I need to treat this as like a bivariate problem. All right. And so here, this gives me a contour of the data points or of the parameters. And then I can also do a simulation to, double check everything and check to see like what the combinations will actually look like. Okay, so here I have a contour plot where it looks like there's going to be a hill centered about here or so. This point here is going to be like the mode of the distribution ish, pretty close. I'm judging this off of the contour lines that we're seeing that the intercept is relatively close to zero, and the slope is between 0 and 1. And we can see the density of the dots just confirming what I'm observing in the contour plot. Also, notice that to help me understand what's going on, the magnitude and the ratio of the coefficients, I put the aspect ratio to 1. So a length of 1 on this axis is the same length vertically also. That, now it's a rectangular box because of the plotting area, but this gives me an easier way to interpret like the ratio of the values. So we can see that we have like less variability in the intercept than we do on the slope off of this distribution. If I zoomed it in completely, it would have been harder to see that. All right, so now let's look at the density of the intercept on its own. And so what I'm doing here is I'm taking my results, but I'm only considering the x-axis. When I do that, And so these are the actual generated points. So this corresponds to the density of the blue dots. And so I can see where, or so this one's for beta. Yeah, this one's for beta one. I can see that it's somewhere around one. And then for, okay, I meant to have beta one and beta zero, but I only have beta one, so we're keep on rolling with it. All right, so I've got, a probability distribution for the beta one now. Now, remember, my ultimate goal is to estimate the LD50. All right, to estimate the LD50 with logistic regression, how we've set this up is that I need to figure out where the probability is equal to a half. Okay. Well, remember that when I'm doing logistic regression, we have the log of the odds is equal to the linear equation part. All right, so the log of the odds, well, the odds is success over failure probabilities. Well, that's going to be 1/2 over 1/2. That's one. Log of one is zero. So what I need to do, I need to figure out where does the beta zero plus beta one x equal zero, solve it for x. And that is going to be where the negative intercept divided by the slope. So what I want to solve is for negative intercept divided by slope. Boom, that's my estimate of LD50. Okay, so let's go ahead and do that. Here I've got negative intercept over the slope. Now I'm going to limit what I'm concerned with to the 95 percentile because we can get some weird outliers that'll kind of warp the visualizations that we're about to do. So I'm limiting things to just the 95 percentile because otherwise things got like too far zoomed out when I was doing the picture. And so we can see the 95 percentile range. And so now I can see a distribution for my LD50. So I see that it's favoring a slightly negative value. And now remember that negative value is the log of the grams per milliliter. Okay, well, let's go ahead and actually estimate it. Now, the histogram is off of the trimmed value, so I'm going to go ahead and use the trimmed mean and the trimmed median. Almost never do we ever use the trimmed median, but I'm going to go ahead and just do it anyway, just to be consistent. And so now I can see that negative 0.37 and negative 0.33 are my mean and median of the LD50. And so now I've got something more complete, more informative, nailed down that I could go and share and report back. Uh, all right. So what we did, we went through the process of estimating LD50 from an experiment where I had too little data to be able to trust the conclusions. Things were not statistically significant. I couldn't trust the results. So I fortified the results using prior distribution that I obtained through subject matter experts by talking to the scientists. After I combined them, I was able to get a better estimate of the LD50 so that way I could deliver to my stakeholders and keep my job. Or I hope that this video has helped you, and I'm going to call it a night. Remember, life is short. Do math.